So let's talk about types of chemical reactions. Most of the reactions that we'll study will fall into one of these following categories, either a precipitation reaction, an acid-base reaction, or an oxidation-reduction reaction. There are other kinds. These are the ones we're going to study. Okay, so we've already been talking about precipitation reactions just a little while ago. So it's one of the most common reactions. And again, a precipitate reaction occurs in an aqueous solution because one of the products is insoluble. So let's look at an example. Precipitate is an insoluble solid compound formed during a chemical reaction. All right, so let's look at this example. So again, we see NaCl is aqueous, and if we, again, just as a reminder, go back and look at your solubility rules. Anything with sodium is soluble. Anything with nitrate is soluble, so both of these are soluble. Na, let's jump over here, NaNO3, they're both soluble. But here, when the silver and the chloride come together, they form a solid. They're no longer soluble, and so a precipitate will form. So that's what it looks like. So we pour the sodium chloride is in this beaker, and then we pour some silver nitrate in. Again, before they're mixed, all the ions are separate, so they're all sort of swimming around by themselves. But when they're all together, the silver and the chloride cannot stay apart from each other, and so they glom onto each other and form a solid. Can't stay dissolved anymore, and so this cloudiness is a precipitate. So we're just going to add, we've already talked about how to write our ionic equations, and now we just kind of have to add one more little step where we need to decide how to predict if a precipitate is going to form or not. And again, it's using solubility rules, but we're just going to do one more thing to figure out what the possible products are going to be. So suppose we mix together nickel chloride and sodium phosphate. All right, so let's just back up. I didn't say if it was aqueous or not, but let's just look at our solubility rules. Most chlorides are soluble. Nickel's not an exception, so this will be soluble. And anything with sodium is soluble, so this will also be soluble. So we've got the ions that we have are actually, I'm not gonna write it out. I'll do that in a second. But I have the nickel ion and the chloride ion, and I have the sodium ion, and I have the phosphate ion. So we already know when nickel and chloride are together, they are apart. I'll go ahead and write that so you don't get confused. And when sodium and phosphate, they break apart into their ions, so they're all swimming around. So we know nickel and chloride can't be a precipitate, and we know sodium and phosphate can't be. However, there's a couple other combinations of these ions. So right now the nickel goes with the chloride and the sodium goes with the phosphate, but we could swap partners. Now the two negative ones won't go together, and the two positive ones won't go together, but now we can swap and put the one positive with the other negative, and then put the two. So what's going to happen is you're predicting what the products are. So how do you tell if a reaction occurs and what to expect? So like I said, we're going to swap partners to figure out what our products are. So let's look at the next slide. So let me go through this a little more carefully. These are our products. So again, I'm just going to show you. So the nickel and the phosphate, but you have to be really careful because I want you to notice nickel and chloride always go together 1 to 2. Why is that? Because nickel is a +2 and chloride is a -1. So there always has to be 2 chlorides for every nickel. We learned that in a couple chapters ago. Same thing here. Sodium is always a +1. Phosphate is always a -3. So they have to go together in that 3-to-1 ratio. However, when they swap partners, we have to, it's like they've gotten new roommates and they have to organize themselves in a way that is appropriate for the new partner. So now when nickel, and don't worry about, I'm not worrying about you see, I'm not worrying about the coefficients yet, and that's because we have to balance the equation before we can do anything else. But all I'm doing is just remembering what the charges are. So the nickel and the phosphate now are going to come together to form a compound. But because nickel's a +2 and phosphate's a -3, they're going to come together with crisscross. So nickel 3, phosphate 2. So they're going to come together in this, even though the nickel over here was just one of them. Now there's 3 of them. Again, it's because the different charges. Chlorine here is chloride is a -1, phosphate's a -3. So they're going to form a different ratio. Same thing here, we've got the Na and we have the Cl negative. Because Na is +1, Cl -1, they're always going to go together 1-to-1. So notice I didn't drag that 3 over there. I didn't drag that 2 over there. They're always 1-to-1 because it's a +1 and a -1. So these are the possible precipitate or possible, these are the compounds that are formed when nickel chloride and sodium phosphate combine together. So notice I didn't worry about the coefficients yet because I'm going to now have to balance the equation. So they've swapped partners. So nickel has gone with the phosphate, but you do have to be careful about the charges and balance out the new charges with each other. And then the sodium has gone with the chloride. So this positive and that last, so it's almost like foil, first and last, and then the 2 in between. But we do always write the positive charged ion first in any compound. Now we're not balanced, so let me do that. So that was the earlier in this chapter. I have 3 nickels here, so I need to have 3. Now once I've got my formula set, I can't change them anymore. So these ratios are because of the charges. These ratios are because of the charges, but I still have to have the same number of each ion on either side. So if I put a 3 in front of there to balance my nickels, now I have 6 Cls. So if I put a 6 in front of there, I have 6 Cls. I also have 6 sodiums, so I'm going to have to put a 2 in front of there, and that gives me 2 times 3 is 6. And then because of distributing, I've got 2 phosphates and 2 phosphates. So this is a balanced equation. So this is called a metathesis reaction sometimes, or an exchange, or sometimes, like I said, I call it the swap your partners equation. So again, this is just highlighting the importance. The important thing to note is the ratio of the ions will change depending on the charges of the ion. So again, nickel phosphate will always form this compound because nickel is a +2, phosphate's a -3. So regardless of how the nickel and the chloride went together or the sodium and the phosphate, the nickel phosphate will have its own formula and the sodium chloride will have its own formula. So be really careful, though. The mistake I see most often is people dragging the coefficients along with it. They don't come along for the ride. You have to rearrange everything. Okay, so like I said, we have to balance the equation. So here's our balanced equation. Now we want to predict if a precipitate will occur. So we use our solubility rules. We already know that's aqueous, and we know that that's aqueous. So we know that those will be soluble. And we also know anything with sodium and chloride are soluble, or most everything with chloride, but anything with sodium are soluble. So we know that's soluble. So now we just have to check this and decide if this is going to be a precipitate or if it's going to stay dissolved. If you go back and look at your solubility rules, most phosphates are insoluble, and nickel is not an exception, so this will be a solid precipitate. So we've added a few little things. So you swap your partners, you rewrite the equation, balance it, and then determine if you have anything that is a solid. And now we do what we were doing before, and we're just going to write everything. So to get the ionic equation, we just write everything that is soluble as the separate ions. And don't forget your coefficient. So this is 3 nickel. 3 times 2 is 6 chlorides. 2 times 3 is 6 sodiums. So again, all 3 of these sodiums break apart separately, and because you have 2 whole molecules, you have a total of 6 ions that are separate. And then we have 2 phosphates. Phosphates are -3, so we have 2. On the right-hand side, because this is a solid, we keep it stuck together. And this one's soluble, so I'm going to break it apart, and the 6 will distribute. So this is my complete ionic equation. And then I can cancel out the chlorine and the sodium, chloride and the sodium. And so my net equation is 3Ni plus 2PO4 -3 gives me Ni3PO4. I think it helps for you to see me writing it out. I know I have this on the next slide, so let's just look at it. So yep, NiCl2 is aqueous, Na3PO4 is aqueous, Ni3PO4 is solid, NaCl is aqueous. And we break it apart into the ionic level. We rewrite it as an ionic equation. So that's what I just did a minute ago. The nickel and the chloride, the sodium and the phosphate. Keep this together because it's solid, and then everything else written. Finally, the spectators cancel out, and you get your essential reaction or your net ionic equation. So again, these take some practice. There is a practice worksheet online if you want to practice a few, and the answers are there as well. We'll probably practice some before the test in our review session. It takes a lot, but it's not hard, you just have a lot to remember. All right, so another kind of reaction is an acid-base reaction. So let's talk real quick about acid-base and what they are. So acids and bases are some of the most important electrolytes. And sometimes we'll probably sometime this semester use an acid-base indicator, which changes colors whether it's in an acidic solution or a basic solution. A lot of common household acids and bases that you're probably aware of. HCl is stomach acid. This is acetic acid, HC2H3O2, so H plus with the acetate ion. That's acetic acid, and that's vinegar, or the acid that's in vinegar. NH3 is ammonia, which is a base. We know antacids are bases right there in their name. They're anti-acids. Sulfuric acid is battery acid, so lots of things. Here's some examples that you can look at. Aspirin is acetylsalicylic acid. Vitamin C is ascorbic acid. Citric acid in fruits, so forth. So an acid-base reaction is generally one, I don't want to say basically, is generally one where a hydrogen ion, H+, is transferred from an acid to a base. So an acid is a substance that, when it's dissolved in water, will yield H+ ions or H3O+ ions, which are called hydronium ions. And water. So what happens is the H plus gets attached to a water, and that's what hydronium ion is. So for example, if you have hydrochloric acid, HCl, it will dissolve in water to give H3O plus and Cl negative. So HCl, the H plus attaches itself to the Cl, to the H2O to give us hydronium, and the Cl negative is left over. So this is an acid-base reaction because a hydrogen has moved from this compound to this compound. This is just showing an example. If you take hydrogen chloride, which is the element or the compound hydrogen chloride, and if you dissolve it in water, you end up with an acid, which is hydrochloric acid. And this is what happens. The H changes over to the H2O to give you the H3O plus and the Cl negative. And so this is the acid. Here's some common acids that you'll want to know. These are considered strong acids, and I guess I'll give you a little preview. Strong acids are those that completely dissociate, so they're parallel to soluble salts. These are acids that completely dissociate in water. So the ones you'll want to know are HBr, hydrobromic acid, HCl, hydrochloric acid, HI, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. So these are strong acids. Any other acid that we have that you know, if anything else is acting like an acid, and how do you know if it's an acid? Generally, it starts with an H. If it's any other acid besides these, they're considered weak acids and they don't dissociate. So that's this next slide. So a far greater number of compounds behave as weak acids and only partially react with each other. And so they would be equivalent to something non-soluble. We keep it written together. So acetic acid is the acetate ion with a hydrogen, and the hydrogen will donate the H plus to H3O to give us H3O plus, and then we have the acetate ion left over, and but only about 1% of acetic acid molecules will ionize, and so generally speaking, we show that with a double arrow because and generally in an ionic equation, if it's a weak acid, we keep it written together. I just want to point out really quickly that most of the time I write acetate like this. This is the acetate ion. Sometimes you'll see it written in different ways, CH3COO negative. Sometimes you'll see it written like that, and sometimes you'll see it written like that. And they're all the same element, or the same compound, I mean. These are all acetate ions. I will most of the time write it like this, C2H3O negative, but I just wanted you to be aware of these because you might see them in textbooks or things like that. So anyway, the double arrow indicates that it's a weak acid and that it will not dissociate very much. And so in general, and we'll do this in a minute, in general, if it's a weak acid, we keep it together. A base is something that when dissolved in water will yield hydroxide ions. Some of the most common bases are those hydroxides from the group 1 and 2 metals, so sodium hydroxide, lithium hydroxide, potassium hydroxide. Again, they break apart into sodium and hydroxide. What's kind of nice about this is that our solubility rules have already covered hydroxides, and so we know that there are 6 strong bases. They're all the ones that are soluble, meaning that they break up 100%, and so we can remember our strong bases. If there's any other base out there that is not one of these 6, they will be weak bases, and again, they're kept together in terms of ions. So this is an example of that. Some compounds produce hydroxide ions when they dissolve by chemically reacting with water. So sometimes you look at something and you don't realize it's a base, but here's why. So NH3, ammonia, is a weak base, And so here's why. When ammonia reacts with water, the water will give it the hydrogen ion to become NH4 plus, and then it produces OH negative. So it is a base also. Even though on first inspection you don't see the OH, it does produce OH negative when put in water. So this also is an acid-base reaction. The hydrogen ion has left from the water, transferred to NH3, so it becomes NH4, and then leaves the OH negative left over. We do a whole lot more with acids and base reactions in the second semester of chemistry. So this is kind of only an introduction to acids and bases. So again, remember that there's the 6 strong acids, and I just want to keep in mind that if you have these 6 strong acids that are below, you always write them as ions when in an ionic equation. Same thing with the 6 strong bases below, you always write them as ions in the ionic equations. If it's any other acid, meaning it starts with a H plus or an H, it will not dissociate, and if you have any other strong bases, it will not dissociate. And let me just point out here, for example, don't forget the 2, so calcium will break apart and give you 2 OHs, and strontium, same with strontium and barium. So, like I just said, you'll find it important to identify if it's a strong or weak acid or base. And like I just said again, if you write an ionic equation, if a strong acid appears in that equation or a strong base appears in that equation, do write them as separate ions, and the bases are easier because it also follows the solubility rules for hydroxides. So those 6 are the 6 soluble hydroxides. So you write them as separate ions. If they're a weak acid or a weak base, represent them as undissociated. Okay, there's 2 types of acid-base reactions that we're going to look at. The first is neutralization reaction. It's the most common. And so this is one of the chemical properties of acids and bases, is that they neutralize each other. So what does that mean? Well, it means that a neutralization takes an acid, reacts it with a base, and the result is an ionic compound or a salt and water. So here's an example of HCN is an acid. KOH, and don't get confused, it does say it's aqueous because it's dissolved in water, but because this is not one of the 6 strong acids, even in an ionic equation, I would keep it written as a whole thing and not break it up. KOH is a base, and then we have the salt. So again, we have our swapping partners. The K and the CN have gone together, and then the OH and the H. So it's just like a swapping partner. The only thing is now that my first and last go together to form water, liquid water. So H and OH form water, and then we have our salt. So the positive ion from the base and the negative ion from the acid will give me my salt. So this is a neutralization reaction. Acid plus base gives me salt plus water. And so a neutralization reaction always involves a transfer of an H plus. So if we look at this example, you can see that what's happening is the H plus leaves the Cl, the HCl, it goes over here and it attaches to the OH, so that's why we get H2O. So the H plus has transferred from the acid to the base. And then we have the potassium and the chloride that are that make the salt. Again, if we want to make sure, because both of these are strong acids and strong bases, we would write the complete ionic equation like this. So let's just remind you, it was HCl plus KOH. Because HCl is a strong acid, I break it up into H plus Cl negative, K plus OH negative, and then gives me KCl, which is a soluble, so I write that separate. and then the H and the OH give me water, and that does stick together. So my net ionic equation, when everything cancels out, will be the essential equation, which is the neutralization. Hydrogen ion plus hydroxide ion gives me water, and that's the neutralization. It's technically a proton transfer. The H plus is moving over. Now, we saw this one earlier, so HCN, like I said, is a weak acid. And so this is still an acid-base reaction. And I think I've got something missing. Let's go back. This was from a few slides ago. If I have the HCN, which is an acid, and the KOH, which is a base, I get KCN, which is the salt. This was from a few slides ago. And so I can see that because this is a weak acid, I keep that together. KOH will be K plus OH negative. KCN, which is soluble, will be K plus CN negative. Let me go ahead and erase that because it's already written. And then the H2O. So you can see what's happened is the K plus has canceled out. So this is my net equation for a weak acid which sticks together. And again, the H plus has moved from HCN to OH negative. So here's a couple other examples. Write the molecular equation and net ionic equation for the neutralization. So we can cancel out the spectator ions and write the net ionic equation. So the spectator ions go away, and there's our net ionic equation. So these are also neutralization reactions, but they kind of get their own little special category because they are acid-base reactions with gas formation. You can think of your your childhood baking soda and vinegar reaction with gas formation. So carbonates react with acids to form CO2, carbon dioxide gas. So here's an example. Carbonate is a CO3, so sodium carbonate and hydrochloric acid. Now what's happening is actually we're still swapping partners here, and we end up with the Na and the Cl, and then actually H2CO3. But H2CO3, which is carbonic acid, is not stable in the water, and so it'll break apart into H2O and CO2. When we have baking soda and vinegar, the baking soda is NaHCO3 and vinegar is HC3H. So, oops, C2. C2. C2H3O2. That's acetic acid. Again, the H's swap. We get H2CO3 and then NaC2H3O2. And the HCO3 breaks apart into H2O and CO2. In a similar way, sulfites will also form SO2. Will also form a gas, SO2, which is that rotten egg smell. So if you have sulfites around, like sodium sulfite in groundwater or something, and then or in ground, like as a solid in the ground, and then you get a little bit of acid or acid rain, you get that bad rotten egg smell. But again, similar thing, the H and the Na swap places, so we get the NaCl. And then we have actually H2SO3, which breaks apart into H2O and SO2. And these arrows just indicate gases.